Hi friends, welcome back. To appreciate the advantages of using appropriate data structures while programming, we just need to understand how the performance of any program can be measured. So there is a measure which commonly used for knowing the performance of any program is the complexity analysis, and commonly it is done with big O notation, though there are many other associated notations like big data and so on. But very commonly used is big O notation. So, what big O notation is, what the complexity analysis is what we just look in short so that in future we can appreciate the use of data structures in performing any algorithm. So there is two important factors we need to look at. One, for any given algorithm, how much time it takes to complete the task. At the same time, how much of the memory it occupies to store the data. So we have two issues to address. One we call time complexity, and the other one we call space complexity. So the time complexity measures how the runtime of an algorithm grows as the input size increases. So it's dependent on the size of the input data we are using. And as the size of the input data is growing, how the runtime of the algorithm is growing is what the time complexity deals with. And it's usually expressed with a big O notation. Of course, there are many other things, but they are more specific to, and we need a very clear cut understanding of the algorithm and accurate measurement we need to do. But Big O is one which is commonly used. The other side, we have space complexity. It measures how much memory usage an algorithm needs and how relatively the requirement of the memory grows as the input size grows. Again, we do use a big O notation for that. Now the question is what the big O notation is. So big O notation, it describes the upper bound of the complexity in the worst case scenario. So for example, if we are searching for a number in a list, the number may be at the first place, the number may be in the middle, the number may be at the end. So if we are searching a number in the list, then it all depends on the luck where exactly that number is. And the moment we get the number, we stop it. Now the question is, how do I represent that? How much time it takes to search any given element. So one we can say best possible thing that is if it is available on the first place itself. So that's best way of doing it. The other thing is the worst case, that is when the element is at the end of the list, then we have to look each one and go till the end. And we are working on comparing two algorithms. then it doesn't make any sense if we try to compare the best cases of each one. What makes sense is compare in worst case which one does fast. That makes more sense. Therefore, usually we prefer to work on the worst case situation, and hence big O notation is commonly used, and it is easier to identify what the worst case could be. So it will be easier to work with big O notation and so on. The issues we have while building any algorithm is the trade-off between the time complexity and space complexity. So what usually we find is when we are building any algorithm, and if we try to reduce the time complexity, then the space requirement grows. Or if I try to control the space requirement, then the whole process slows down. So there is inverse connection between the time and the space. If you try to reduce the time, space goes up. If you try to reduce the space, then time goes up. Then we need to find some optimum balance between time and space so that both of them are at their optimum. So that's what we have to worry much when we are deciding appropriate data structure for any given algorithm. So some data structures will improve the time complexity. Some of data structures will help in reducing the space complexity, but not all. So there is a trade-off between them. So we need to identify the best possible data structure that somehow balances both of them, doesn't allow anyone to go to the extreme. So that's one we need to look at while understanding the data structures and how data structure plays important role in controlling time as well as space complexities of any algorithm. Yeah, just talking uh, doesn't make any sense unless we put that in the graphical form. There are many possible uh, uh, complexities. It can be a constant one. That means whatever be the size of the data, it takes a constant time to solve the problem. Like finding the first number. So whatever be the size of the data, finding first number needs only a constant amount of time. So that is what we call O of 1. Some algorithms will take logarithmic uh, complexity. So as the size of the input n is increasing, the computation increases logarithmically. So it is called order of log n. So there are some issues where it increases linearly, then log linear, then quadratic, then exponential. The worst case is factorial. So there are so many different possible time complexities we have, and you can just see how the things are growing. So linear one, as the size n increases, the number of computations linearly increase, and quadratic means as the size increases, the number of computation increase to the square of the numbers, and so on. So that's what the complexity is all about. So overall, what are we working at is the worst possible thing in this given situation is factorial, and say one data structure can get an algorithm work in factorial. And if you can find another data structure that can make the same thing work in exponential, then definitely it is better to switch to the new data structure that is exponential compared to the factorial one. Same way, if it is linear, and you find something which is logarithmic, definitely logarithmic is far better than linear. And if it is constant, nothing like that. So if you can make something work in constant time, of course, nothing better than that. So these are the different possibilities which are commonly found when we are dealing with algorithms, the time complexities, and same thing applies to the space complexities also. Here the x component is input size n, whereas the y component is memory size requirement. Yeah, they again we have similar thing. So to understand how they differ. So let's just take a few examples that the n can be 1 or can be 10,000 million and what do you say billion. So if it is a constant time activity, then whatever be the size of the input, we are going to get a 1 unit time to solve the problem, like finding the first element in the list. So whatever be the size of the list, getting first element, definitely it is going to be of unit time. Now, the same thing, if we are working with any algorithm that needs logarithmic time, so for one, it takes 1 unit of time, for 10, it may be using 4 units of time, for 1,000, it takes 10 units of time, for 1 million, it takes 20, for 1 giga, it takes 30, and so on. So that means as the input size gets multiplied by 1,000, the logarithmic scale gets added by 10. So multiplying n by 1,000, we'll just add 10 to the log n. So when we are working with any algorithm, and if that algorithm works in order of log n, then it's a best possible thing because as we no, that we are talking about searching algorithm. Then there is something called a binary search algorithm, and this one is useful when we have a sorted list instead of any general list. If we have a sorted list, then we can make use of a binary search, and this binary search will work in the with the time complexity of log n. Now, what happens is if there are, say, 1,000 data in our input, and if it takes 1 unit of time or 10 units of time, to say, for example, then instead of 1,000, if we make 1 million data, then with 1,000, it was working in 10 units of time. Now with 1 million, it works in 20 units of time. Just 10 units of time will increase, even though the size is multiplied with 1,000. The input has grown thousandfold, whereas the requirement is changing just by addition of 10. So that's a advantage of working with a logarithmic. A linear, same, whatever is n, 1, 10,000, million, billion, and so on. And if it is 2 to the power n, that is exponential, then for 1 it takes 2 units of time, for 10 it takes 1,000 units of time, and 1,000 onwards, it's just beyond our computation. So it's so big, then it's just a universal lifetime. Even that one doesn't fit here. So we can't think of any algorithm which works in uh, exponential time in our real sense. So if it is any exponential thing, then we should be working or we should be happy with a small input size only. Can't expect to work with real time problems. So these are the different things we are about to see. So why we are looking at all these things is if we can select an appropriate data structure, then some of the algorithm instead of this order can become this order so that now every type of problem we can find a solution, or instead of linear if it becomes logarithmic, then you can see how much reduction is there in the requirements. So just 10, 20, 30, the just addition of 10, even though the input is being multiplied by 1000. So that's advantage of working with logarithmics complexity. So let's take an example. So we are doing something. So for doing just something once, it just takes 1 unit of time. Instead of that, that same something, if we repeat n times, so we have just put that in a loop and we are repeating that something, some action for n times. That means the worst case, we are going to have the time complexity as order of n. Now we are repeating that under two loops. So one outer loop from 1 to n, then inner loop from 1 to n. That means for every I, j repeats from 1 to n. Therefore, in all, the this something is repeated n times for every I, and I is repeating n times. Therefore, in all, the order of this is the order of n square. And same way it grows. Now we have three loops, nested loops, loop in, loop in, loop. Then of course three times. So the inner loop repeats n times. Then the next loop makes the inner loop repeat n times. Then the outer loop repeats the inner one n times. So in all, we can say that this whole thing is working n cube times. Now, if we just look at this only three different or the four different operations we have, what we can say if there are 1,000 numbers, if there are say 1,000 numbers, then what we can say is if you are trying to do some simple work like finding the first number of the 1,000 numbers, it's just a one step activity. So that's the order of one. Or you are trying to search something in that list, then definitely you will do from first to last, you may have to go. So it will take worst case n steps to reach the end. So that will be order of n. And same way, if you are talking about arranging the n numbers in order, then you may have to do some type of sorting, and common sorting algorithm is repeated n square times. So this is the order of n square. Something like matrix multiplication and all that. So they do require three nested loops. Then it's order of n cube. So makes no sense as long as we just keep talking in n n n. Okay, let's take n as say 1,000. So we have a list of 1,000 numbers, and if you want to find first element in that 1,000 numbers, so that's simple one step answer. order of one, no issue. Now want to search one element in that thousand element data, then each one you check it, then it takes maximum thousand steps because you may have that element on the end. So that you need to check all the thousand elements, or it may not be there in your list. So to say that it doesn't exist in the list, you have to check each one. So move out of the list, only then you can declare that it doesn't exist. So whatever it is, it's every element has to be checked. So it's order of n. You want to put that, that means thousand times you need to do that. Now you want to arrange these thousand numbers in order. If you want to arrange these thousand numbers in order, then it is n square. So that is thousand by thousand. That means 1 million times we need to work on this. Just because there are thousand numbers in the list, we need to work for 1 million times. And if you assume that instead of 1000, if there are 1 million, then 10 to the power 6 square, then we need to work for 10 to the power 12. That is 1 trillion activities we have to do. So you just imagine how much time it takes if there are 1 million data in our list. Yeah, it does make sense today because today we are in the world where we deal with big data and all that. Having 1 million data or 1 billion data is not a big issue today. So therefore, just converting order of n square algorithm down to order of n can save a lot to us. Now, getting to the third type where we are talking about matrix multiplication like action. So we are talking about, say, 1,000 by 1,000 matrices are being multiplied. So 1,000 into 1,000 into 1,000. So that is uh, 10 to the power 3 into 10 to the power 3 into 10 to the power 3. That means 10 to the power 9. 1 billion activities we have to perform to make sure that 1,000 by 1,000 two matrices are multiplied. Now that 1,000 by 1,000 matrices, if they get into a million by million, then I don't know where it goes because matrices, as we discussed somewhere else, it's somewhere used to represent a graph and all that. So if you are talking about real-time situation of today, if you are talking about cities, interconnectivity and all, definitely you may be talking about thousands of cities or millions of cities, or you're talking about a computer connectivity, internet connectivity and all, then having millions of nodes in the internet is not a big issue today. So million by million, and that is, if you just look at that, I don't think where we end up. So any data structure, if it can get order of n cube down to n square, you are saving a lot. So the one which cannot be processed can be made somewhat possible. Or if you can convert order of n square down to order of n, of course, we are going to save a lot. And if you are going to reduce somewhere order of n down to order of 1, then that's the best, nothing better we can expect. So that's where our data structures help in. So if we look at the problem carefully and decide the best possible data structure, then we could reduce the time complexity, we could reduce the space complexity, and if we can reduce that even by one order, then we are going to save a lot in terms of space as well as time. So that's some inputs regarding how data structures will influence the time and space complexity of any algorithm. And that also conveys an important message that why data structures are so important in life of any computer engineer. So that's it for now. More details to follow. Thank you.